Hello and welcome to our review of the final part to our Chapter 9 on quadratics. We spent a fair amount of time on this. Remember at the beginning we looked at the basic equation and found the axis of symmetry and made the shape of a graph called a parabola. In the middle there we looked at the two other forms besides standard, so we could see the zeros or roots and also the vertex form and intercept or factored form. And now we're looking at just solving equations that have x squared and x in it. They're a little bit tougher than linear equations, and we're going to start off with a couple of problems here and end with some stuff using the quadratic formula. All right, so we're looking at a problem here where we're solving an equation, and to solve this equation we need to do the order of operation. We want to make sure we're using our order of operations in reverse order to solve. So I'll start with this number 1 here. We have addition or subtraction to undo. There's no parentheses. We add to both sides. We get 2x squared equals 8. We have multiplication or division. There's no more addition or subtraction, so we divide. We get x squared equals 4. And now a step that we haven't had to do until just recently, undoing exponents. And the way we undo the exponent of 2 is we square root, remembering that the value we squared had to equal 4. That means positive 2 or negative 2 could have been squared. If we go back and check our values here, if you take 2 or negative 2, I'll put negative 2 here. Negative 2 squared would equal 4. 2 times 4 is going to equal 8. And then 8 minus 7 would equal 1. So 2 and negative 2 work here. Let's look at this other problem. Notice this problem has parentheses and a squared value. We're going to have to undo our exponent first. So undoing exponents in this case means taking the square root, and we'll get the stuff that's inside. Square root of 1 is 1, so we have positive and negative 1. These are two different values we need to evaluate as separate equations. So 2x minus 7 could equal 1, and 2x minus 7 could equal negative 1. Undo the minus with a plus, and divide by 2. We get x equals 4. We come over here and add 7 to 1. We get 2x equals 6, dividing by 2. We get x equals 3. Notice different values here, but if we plug into our original equation, we get 2 times 4, that's 8. 8 minus 7 is 1. 1 squared equals 1. And then 2 times 3 is 6. 6 minus 7 is negative 1, and negative 1 squared is also 1. Okay? And what you're going to find in the rest of these problems is we're going to get to a point that looks similar to these, and then we'll finish using these methods, but we have to do some work to get there. This one isn't set up quite like the previous ones, but we can get it to that point. We notice that we have an x squared and an x. These are not like terms, although it's the same variable. You can't combine them. So we need to find this way to create the perfect square trinomial, and you do that by cutting the coefficient of b in half and squaring it. So half of 10 is 5, squared is 25. We add that to both sides. It's an equation. And because of that, we're allowed to rewrite these three terms as a single x plus something squared equals 4. And that answer is a 5. It's half of the 10. That comes out of what happens when you FOIL. You'll double the 5 to get the 10, so we work backwards. On the right side, negative 21 plus 25 equals 4. Now we're ready to solve the problem like we did on the previous slide. We simply take the square root of both sides. We get x plus 5 equals, and the way to think about this, it's not really just the square root of 4, it's what number squared equaled 4, and that answer is positive or negative 2, so that causes us to have to write two equations. X plus 5 equals 2, and if x plus 5 equals negative 2, it's a solution. Subtracting 5, we get x equals negative 3, and subtracting 5 here, we get x equals negative 7. If we plug that back into the original equation, we would see that it works. I'll just pick one of them. I'll pick the negative 3. That'll be a 9 minus 30. That's negative 21. Same with negative 7. You can check that. And now let's try another one. Let's try this number 4. You can try it on your own if you'd like. Notice that we don't have the x squared and the x by themselves on the left side, so our first step is going to be to subtract 17. In that case, we end up with x squared minus 8x plus whatever it takes to make a perfect square equals negative 17. And we're going to take half of negative 8, that's negative 4, and square it. That makes it a positive 16. If you add to one side of an equation, you have to do it to the other side. This creates this perfect square we call trinomial, which will turn into something with parentheses. And then, of course, negative 17 plus 16 is what we have to create x minus something to equal. So in this case, half of negative 8 is negative 4. And to undo this, this is like the previous slide, we have to square root, and this is where the problem comes in. You can't take the square root of a negative without another set of numbers called complex or imaginary. So we get x minus 4 equals the square root of a negative number. There's no real solution there, so we would simply say no real solution. Here's a lot of information that was given in the book that I thought was worth having a look at. You can hit pause and go through it again. We're going to use the information that we get from the discriminant, the square root material we see, to decide how many solutions, and then from there we can figure out what the solutions are if there are any. So for instance, here's a quadratic equation. We've got a of 1, and I'm going to write out what those values are. B is negative 8, and C is 18. When we plug into the discriminant, we'll get negative 8 squared minus 4 times 1 times 16. That's 64 minus 64, which is 0. And if we remember back from the descriptions here, when the discriminant is 0, we just have one solution. So when we come in here, we'll be able to just plug in to our quadratic formula. X equals negative b plus or minus the square root of the discriminant. That's 0 in this case, and so we'll end up with just one solution. Negative 8 is positive 8. 2 times 1 is 2. And we get an answer of 4. Just one solution. We could think of it as a double 0, a double root. What that means is at x is 4, this thing, whether it opens up or down, in this case it should open up, just hits the x-axis in one place. Moving over to the other side here. Similar problem, only in this case we need to get our equation in standard form, ax squared plus bx plus c. That allows us to find a, b, and c. In this case, b is 4 or negative 4. And a is 2, c is 6. When we follow through on the math here, we get 16 minus 48, negative 32. As we saw in one of the previous problems, that's no real solution. Okay, so here's a quadratic equation. It is in standard form, so we can just start looking at the a, the b, and the c and see what we got for a discriminant, how many solutions. In this case, negative 5 squared minus 4 times 3 times 1. That'll give us 25 minus 12, and that's 13, a positive number. I expect 2 solutions. Those solutions we'll go ahead and figure out. And since we know what our discriminant is, we actually know a part of the quadratic formula, that it'll be 13. So when I go to write this, I get the solution. We have a quadratic equation set equal to 0. The quadratic formula can be applied here. So we have negative 5 plus or minus the square root. We've already figured this out, 13, all over 2 times 3. 5 plus or minus the square root of 13. The square root of 13 is not a convenient radical. It's not a perfect square. So we can leave it like this. You could use a graphing calculator or a calculator to get a decimal form. But here's our 2 values. Another way of saying this is x equals 5 plus the square root of 13 over 6 and 5 minus the square root of 13 over 6. But either form is fine. You'll probably leave it in the plus or minus form. If you have any questions, make sure you ask them, and good luck on the test.